Beneath Antarctica's vast white expanse lies a world of hidden signals and fleeting habitats that challenge everything we thought we knew about the planet's coldest reaches. Deep within the ice, up to 2 kilometers beneath the surface, an international array of buried rod antennas has detected a precise electromagnetic pulse, a 0.2-second blip repeating every 7 minutes. This strange rhythm hints at powerful forces, subglacial stresses, and meltwater flow playing out far below our feet. Meanwhile, atop the ice during warmer intervals, seasonal meltwater ponds, once dismissed as mere melt features, are now recognized, thanks to groundbreaking MIT research, as sunlit sanctuaries for microbes. Fueled by solar heating, mineral-rich dust, and geothermal warmth, these ephemeral pools harbored life when most of Antarctica lay locked in ice. Though one discovery unfolds in near-eternal darkness and the other under transient sunlight, both reveal nature's subtle frequencies, electromagnetic and biological, and remind us that even the iciest realms teem with processes waiting to be understood. Radio waves are electromagnetic ripples that can penetrate ice and rock, offering a non-invasive probe of hidden terrains. In Antarctica, thick ice sheets, up to 4 kilometers deep, block light, snow, and even drilling efforts, but not low-frequency radio. Beginning in 2015, an international team deployed the ICETADAR array, over 50 solar and wind-powered stations scattered across West Antarctica, each equipped with ultra-sensitive antennas covering 0.3 to 1 megahertz. These stations continuously record, compress, and satellite uplink data to labs in the US, Germany, and New Zealand. During a routine algorithmic sweep of months of recordings, researchers noticed a perfectly periodic pulse, lasting 0.2 seconds and repeating every 7 minutes. Too coherent to be atmospheric noise or human activity, the blip hinted at a deep Earth phenomenon waiting to be decoded. Once the rhythmic blip was flagged in months of ICETADAR array data, the race was on to pinpoint its origin. In mid-2025, a field team endured sub-zero winds and crevasse-strewn terrain to deploy 3 mobile drill rigs, each housed in insulated shelters. Over the painstaking weeks, technicians melted boreholes through nearly 2 kilometers of ice, lowering cryogenic receivers equipped with custom low noise amplifiers and temperature sensors. Simultaneously, ground-penetrating radar units swept the area with 50 megahertz pulses, mapping internal ice layering, while magnetotelluric sensors recorded natural variations in Earth's magnetic and electric fields to infer rock conductivity beneath. Back at base camps, data engineers synchronized time-stamped logs from all instruments. Using travel time differences of the radio blips across multiple stations, they applied beamforming algorithms akin to those in radio astronomy to triangulate the source within a 500-meter radius. The convergence of radar-derived subglacial channel maps and conductivity anomalies from magnetic tellurics pinpointed a network of water-filled fractures beneath Thwaites Glacier. This integrated approach transformed an enigmatic signal into a geospatial target, laying groundwork for direct sampling of subice hydrology and offering a blueprint for future polar geophysics campaigns. With the source localized, researchers dove into signal processing. Each 0.2-second pulse was extracted using high-resolution Fourier transforms, revealing narrowband peaks at 0.45 MHz with sidebands spaced at 0.02 MHz intervals. Clear evidence of modulation. By analyzing the Stokes parameters, they tracked the polarization vector's gradual rotation over each cycle, indicating that the ice's crystal fabric and transient water channels were acting as dynamic waveguides. Advanced filtering removed anthropogenic noise, while machine learning classifiers flagged anomaly patterns correlating with spikes in meltwater flow measured by temperature and pressure sensors in boreholes. The most striking finding was the pulse amplitude's strong seasonality. It climbed by 30 to 50% during the austral summer, when average subglacial temperatures rise above 2 degrees Celsius and meltwater production peaks, and then diminished as the ice refroze. Cross-correlation analysis showed a Pearson coefficient of 0.82 between meltwater discharge rates and radio wave strength. This discovery positions the radio pulses as a near real-time proxy for subglacial fluid dynamics, offering insights on minute-to-minute scales that satellite altimetry or GPS cannot match, and opening new avenues for predicting ice sheet responses to climate warming. beneath the ice's frozen veneer to rival explanations, vie for the radio pulse's source, and each carries profound implications. The first posits a geological origin. Deep below the bedrock lie quartz-rich fault zones. Under the immense weight of the overlying ice, these crystalline structures deform and fracture, generating tiny electric charges through the piezoelectric effect. As stress accumulates and releases, whether from slow tectonic creep or diurnal temperature shifts, bursts of energy radiate outward as the precise 7-minute blips we observe. If true, Antarctica's subsurface heartbeat could serve as a real-time monitor of tectonic and glacial loading cycles, shedding light on how the ice sheet itself influences seismicity and crustal stress. The second hypothesis points to subglacial hydrodynamics. Networks of meltwater channels meander beneath the ice, driven by summer melt and geothermal heat. When channel dimensions fluctuate, opening in high-flow pulses and collapsing as pressures change, they generate transient electrical currents as ionic-rich water surges through rock fractures. These currents, in turn, emit radiofrequency pulses with the same periodicity tied to pulse wave propagation through the fracture network. Confirming this would transform the signal into a minute-by-minute gauge of meltwater routing, a breakthrough for predicting ice sheet acceleration, basal lubrication, and downstream sea level contribution. Either mechanism heralds a new era of real-time cryospheric monitoring. Unlike satellite radar altimetry, which updates surface elevation only every few days, radio wave sensing responds instantly to subwise changes. Research teams are already modeling how these signals could feed directly into climate projections, adjusting parameters for ice viscosity, basal drag, and meltwater flux. In practical terms, coastal planners could receive early warnings of rapid ice stream surges that threaten to calve massive icebergs, while oceanographers refine circulation models to account for pulsed freshwater injections. Ultimately, this discovery blurs the line between geology and hydrology, offering an unprecedented window into the hidden dynamics sculpting Antarctica's future and, by extension, our own. In a groundbreaking paper published this spring, MIT glaciologists and astrobiologists revealed that seasonal meltwater ponds atop Antarctic ice sheets may have provided stable sunlit oases for microbial life during past warm periods. Using a combination of satellite altimetry, drone-mounted spectrometers, and sub-ice coring, the team mapped the distribution, depth, and duration of these ephemeral ponds over the last 10,000 years. Their data show that, during Holocene thermal maxima, thousands of shallow pools, some up to 2 meters deep, persisted for weeks, sheltering microorganisms from the crushing pressures and perpetual darkness of subglacial lakes. Geochemical analyses of ice cores drilled near the transantarctic mountains uncovered organic biomarkers and DNA fragments consistent with cold-tolerant bacteria and algae, suggesting that these ponds were not just transient melt features, but biologically active habitats. How did these meltwater ponds form and sustain life in Antarctica's extreme environment? During summer months, solar heating and katabatic winds drove localized melting on rock outcrop edges and blue ice zones, creating shallow basins. Windborne dust and mineral particulates delivered essential phosphates and iron, while atmospheric deposition supplied nitrogen compounds. Sunlight, penetrating clear water, enabled photosynthesis by psychrophilic algae, generating oxygen and organic carbon. Meanwhile, geothermal heat fluxed through the underlying bedrock, maintained liquid water at the pond bottoms long after surface temperatures dropped. These combined factors, liquid water, sunlight, and nutrient inputs, created miniature ecosystems, alternately freezing over at night but thawing each day, enough to allow metabolic activity and cellular replication. The MIT study's revelation that seasonal meltwater ponds once dotted the Antarctic surface carries profound implications far beyond our planet's southernmost reaches. On Mars, satellite imagery has long hinted at ancient paleo-like stride basins, etched with mud cracks and mineral halos. If Antarctic melt ponds sustained cold-tolerant algae and bacteria, Mars's transient surface liquids could have hosted similar microbial refuges. Future rover missions targeting former Martian lakebeds, such as Jezero, Crater, might prioritize locations where orbital spectroscopy detects hydrated minerals, analogous to Antarctic pond sediments. Closer to home, icy ocean worlds like Europa and Enceladus warrant renewed attention. Tidal flexing and cryovolcanism on these moons likely generate surface melt or subsurface pools heated by radiogenic decay, creating environments where Earth's pond-dwelling extremophiles could survive. By comparing the genetic and biochemical signatures of Antarctic microbes found in ice core biomarkers, astrobiologists can refine life detection instruments, sequencers sensitive to lipid membranes, and photopigments that fluoresce under UV light. Laboratory simulations are already using Antarctic pond isolates to test microbial viability under simulated Martian UV flux and Europa-like saline chemistries. Back on Earth, meltwater ponds are not merely historical curiosities, but active players in modern climate dynamics. During austral summers, contemporary ponds cover tens of thousands of square kilometers of blue ice zones, absorbing solar radiation and accelerating local melt in a feedback loop. Embedded microbial communities produce greenhouse gases, methane, and nitrous oxide during metabolic bursts, each thaw cycle. Although individually small, the collective emissions from Antarctic ponds could represent a non-negligible component of polar greenhouse budgets, especially under warmer future scenarios. To quantify this effect, researchers are deploying autonomous sensors, submersible fluorometers, microscale gas analyzers, and time-lapse cameras in selected pond networks. Data streaming via satellite will feed into coupled cryosphere models, enabling real-time projections of melt pond-driven albedo changes and biogenic gas fluxes. These enhanced models will sharpen sea level rise forecasts by accounting not only for ice sheet dynamics, but also for biogeochemical feedbacks at the ice surface. Ultimately, the convergence of astrobiology and climate science in meltwater ponds underscores a unifying theme. Wherever liquid water persists, fleetingly life exploits it, and in exploiting it, influences its environment. By studying these ephemeral Antarctic oases, we learn not just about Earth's past and future climate, but also gain templates for searching life across the solar system and for understanding how tiny organisms can sway planetary processes on a grand scale. We began by listening for radio pulses deep beneath Antarctica's ice, and discovered a rhythmic signal tied to subglacial stress and water flow. Now, we've seen how on the surface, seasonal meltwater ponds once provided sunlit sanctuaries for ancient microbes, microhabitats that punctuated the ice's seemingly barren expanses. Both revelations highlight Antarctica as a dynamic frontier where physical forces and life intersect. Governed by hidden frequencies of energy, water, and chemical exchange, as we refine our listening tools, radio arrays, spectrometers, DNA sequencers, we not only decode Earth's past, but also sharpen our search for life in the cosmos. These intertwined stories remind us that even the planet's coldest reaches teem with signals waiting to be heard, and that each discovery brings us closer to understanding life's resilience in the face of extreme change. Have you enjoyed these discoveries? Like, subscribe, and comment below on your favorite, so you won't miss our next deep dive.